In this video, we're going to learn about the ratio test. The ratio test involves the ratio between the n plus 1th term and the nth term. So between a term and the next term is what that means. First thing we have to do is find the limit as n approaches infinity of the n plus 1th term over the nth term, and we need that to be an absolute value. So after we find that limit, we compare it to we compare it to 1. If the limit is less than 1, the series converges. If it's greater than 1, it diverges. And if it's equal to 1, then our test is inconclusive and we have to do a different kind of test to see if it diverges or converges. So here's an example. Use the ratio test to determine if the infinite series 1 over n converges. This is the harmonic series, just to remind you. So using the ratio test, we have the n plus 1th term, so we're going to plug n plus 1 in for n, so we get 1 over n plus 1, and then over the nth term, which is just the general term, so 1 over n. And then before we take the limit, we'll just simplify this a little bit. So we have a fraction divided by a fraction, which means we have the numerator multiplied by the reciprocal of the denominator. So we're just taking this denominator and flipping it over. And then you multiply straight across, so I get n over n plus 1, and then we can do the limit as n approaches infinity, so the plus 1 doesn't matter anymore, which means we have n over n, which is just 1. And that means it's inconclusive, so we can't, the ratio test doesn't tell us anything, and we have to do something else to figure out if this converges or diverges. So by the p-series test, I know that this diverges because 1 over n to the first power, p equals 1, is less than or equal to 1, so p-series means it diverges, and it's the harmonic series, so I know for sure it diverges. Here's another example using the ratio test. This time we're determining if this alternating series converges. We could use the alternating series test on this if we wanted to, because it's an alternating series, but we can also use the ratio test. And the ratio test is really nice because these absolute value bars are going to get rid of those negative ones for us, so it sort of makes it not alternating anymore. The limit as n approaches infinity of the n plus 1th term, so we're plugging n plus 1 in anywhere there was an n, so 3 to the n plus 1. And then with this one you have to be careful. It's n cubed is the original series, so the n plus 1th term is going to be n plus 1, like the quantity cubed. Don't just stick a plus 1 after the n cubed. So it's quantity n plus 1 cubed. And then the bottom is the same as our series. Then we can simplify this. So like I said, the absolute value bars take care of the negative ones. Everything else is going to be positive, so we can just leave those. We don't need the absolute value bars anymore. And then alright, so let's mark things out. So we canceled out those because the absolute value bars. And then the next thing that happens is that the numerator stays how it is, and the denominator, we multiply by the reciprocal of the denominator. So now, when we multiply, we have the 3n here, cancels out with the 3n there, but it still leaves us with a 3 to the first power. And that gives us this right here. So we have 3, because we had 3 to the first, so we have 3. And then n cubed from here, and then the bottom is just n plus 1 cubed. So if we take the limit of this, I have 3n cubed on top, and I have an n cubed on the bottom, so the n cubed cancel each other out, sort of. And this is only because it goes to infinity. It's not really good notation to write it like that, but we end up with the limit is equal to 3, and that is greater than 1, so that means that our series diverges by the ratio test. Here's one for you to try. Use the ratio test to determine the convergence of the series e to the 4n over n factorial. And remember, n factorial is just n times n minus 1 times n minus 2, all the way to 2 and then times 1. So you're just going all the way down. That's what n factorial means. Alright, pause the video here, and when you're ready, we'll look at the solution. Alright, so here we have the ratio test for e to the 4n over n factorial. When we're doing n plus 1, remember we're replacing this quantity of n with a quantity of n plus 1, so this needs to be in parentheses. Same thing for n factorial as n plus 1 factorial. and then the denominator is the same as the series. The absolute value bars are not important in this one because there's no way to make this negative. It's always going to be positive, so we don't have to write them. It's not wrong if you do write them, though. That's fine. Alright, so I have my numerator times the reciprocal of my denominator, and now I can start canceling things out. So I have e to the 4n cancels with the 4e to the 4n here, but we still have e to the 4th. And then n factorial cancels out with the factorial here and just leaves us with the n plus 1 part. So now when we multiply what we have left, we get e to the 4th on top and n plus 1 on the bottom because everything else is canceled out. So the limit as n goes to infinity, I don't have an n on the top, that's just a constant. So my my denominator is going to infinity, which means I have something small over something gigantic, which gives me 0. And 0 is less than 1, so that means our series converges by the ratio test. That is the end. If you have questions, please ask.